I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
Welcome to Introduction to the Moon. This is the first lecture in the Moon 101 series, and it's designed to give you a brief overview of a lot of different subjects about the moon that other lecturers will go into in more detail in the successive lectures. My name is Dean Epler. I'm a retired NASA lunar geologist, and I'm presenting this material, although it was originally put together by Paul Spudis, the scientist who originated the whole Moon 101 concept about 10 years ago. Paul has passed away, and I'm trying to fill in for him, hopefully in such a way that he will not be disappointed. So the first important part that we need to discuss is really what the moon is. And the real key, I think, is that the moon is a planet. It has many of the features that we think of as a planet, as in having a core, having a mantle, having a crust. No other planet is as proportionally large as the moon is with respect to the size of the Earth. Many of the other planetary bodies that have moons, such as Mars, have small irregular moons that seem to be just sort of, accidentally captured into the orbit of their primary body. The moon has a heavily cratered surface. It is partially flooded by lava flows, which erupted somewhere between 4 billion and about 1 billion years ago, with the bulk of the lava being emplaced around 4 to 2.2 billion years ago. Since the moon has formed, there have been many impacts by comets and asteroids, and they have radically altered the outer surface of the moon. It has created what is a chaotic upper layer of debris, which we call regolith, and it has deeply fractured the lunar crust to a depth of over 10 kilometers. By and large, the moon was a dead planet by about 1 billion years ago. There's a lot we don't know about the history of the moon, and some of these unknown items are key to understanding the history of the Earth-Moon system. The moon is covered by a particulate blanket, and I say particulate blanket because it is really a mix of particle sizes all the way from extremely tiny sizes all the way up to boulders that are the size of a building. It is easily accessed. It is a likely feedstock for resource extraction. And if you look at the picture of John Young's feet, this picture was taken on Apollo 16, you'll see that there is actually dirt, fluffy dirt regolith kicked up around it, and it gives you a nature of how loose and fluffy the upper layer of the regolith is. But in the upper right corner, you see the picture of an extremely small, but nevertheless almost perfect crystal of a mineral. The moon's regolith is full of things like this. As I said, it goes all the way from large rocks down to the finest fraction that you can imagine. I want to go into some general properties. On the left is the moon, in the center is Mars in red, and on the right is Earth in blue. And if you compare the numbers for any given variable across the graph, you're going to see that the moon and Mars are actually a lot more like each other than Mars is like the Earth. A lot of people have taken the view that Mars is more like the Earth, and to a certain extent, that's justified in light of what we think the early Martian history is now, in that we think it was warm and it was wet. But the size of the planet, its composition, its very nature makes it actually a lot more like the moon than it is like Earth. The moon has a history. Before Apollo, it was dubbed the Rosetta Stone of the planets. And after Apollo, in the immediate years after Apollo, a lot of people sort of wondered, well, was it really? But as time has gone on, and as we've analyzed lunar samples, we've come to believe that moniker, in fact, is absolutely correct. And much of what we understand now about the other planets in the solar system as well as the Earth. We've learned because the moon has preserved a history that many other planets no longer have. Now, before we went to the moon on Apollo with human beings, we had quite a bit of precursor missions from the United States. In addition to that, the Soviet program landed a considerable number of spacecraft on the surface, as well as flew vehicles around it. Before we could even think about landing on the moon, we had to understand what the moon was actually like on its surface. And it's really important to recognize that before these vehicles went to the moon, the smallest thing we had ever seen on the lunar surface through terrestrial telescopes was about 1 kilometer on a side. And the questions we had before we sent these spacecraft there seem somewhat silly now, but there were things like, where do craters run out? Are the craters all the way down to the smallest size? Are there rocks on the surface? Is the surface capable of bearing the weight of a lunar module? All of these things now we understand, perfectly well. But before we went to the moon with people on Apollo, we didn't know any of that, and this set of robotic missions clarified that. And I'm going to talk about each one in turn. The first successful spacecraft that basically touched the moon was the Ranger series. The Ranger series were hard landers in that they had no other, I suppose you could say, objectives other than hitting the surface and imaging the surface all the way down. As such, the only thing they did was photograph the surface. But this was really key because prior to the Ranger set of missions, we simply had no idea what the surface was like at a human scale. Ranger answered a tremendous number of questions that, frankly, we had had since Galileo first turned his telescope to the moon. There was a whole variety of soft landers, which, for obvious reasons, did a lot more when they got to the surface than the Ranger did. The Surveyor was an American mission. It flew 7 total spacecraft in the series, of which I believe 4 were successful. The whole purpose of the Surveyor missions was to safely soft land on the moon, to understand the nature of the lunar surface, and to do some basic chemical analysis. But largely it was, you can think of it as largely a civil engineering mission. What we wanted to know is, A, can we land on the moon? Is it possible to have a spacecraft, fly to the lunar surface and survive? The second thing is, what is the surface like? Is it soft? Is it a hard rock? What is it like? Is it like a snowbank that we'll disappear into? And the Surveyor was an incredibly successful set of missions that we're still analyzing data from. The Soviets, in addition, flew 3 sample return missions to the moon in the 70s. The Luna 16, 20, and 24 missions not only brought back samples from places we did not go on Apollo, they did it robotically. And at this point, no other country on the Earth has robotically recovered a sample from the lunar surface. In addition, the Soviets landed 2 Lunokhod rovers, which were incredibly successful. They drove around the moon's surface, again in places that the Apollo missions hadn't gone. And the 2 sets of Soviet missions greatly enhanced what we understood from Apollo by simply providing complementary samples from other places on the moon the Apollo program did not get to. Lastly, Lunar Orbiter was another really key mission because it circled the moon and photographed about 75% of the surface. Up to the point of the Lunar Orbiter missions, the only real global view of the moon that we had was from telescopic observations, and telescopic observations that simply do not see the lunar far side. Lunar Orbiter was a mapping mission. It was intended to collect global mapping data that the Apollo program could use in planning landings. Now recently, and I say recently within the last 10 years or so, we have been flying, not just we, the United States, but the human race has been flying a significant number of orbital missions around the moon. Countries that had never done this before, like China, Japan, India, have flown a number of really successful missions and again have enhanced our understanding of the moon's surface. In addition to that, The Chinese have landed a soft lander with a rover in a manner not dissimilar from the Lunokhod missions. Okay, the first mission I want to take a look at is Selene. This was flown by the Japanese Space Agency. It carried a variety of instruments on board with three general objectives. First was to photograph the surface. Before the Selene mission went, we did not have any better resolution of the surface than we had on Apollo. The Selene mission improved that considerably. In addition to that, it carried geochemical remote sensors, basically instruments that could look down at the surface and capture radiation that would tell us what the composition of the lunar surface was. And in addition to that, it carried instruments to look at the nature of the space at the orbital altitude of the spacecraft. Chang'e 1 was a Chinese instrument and carried much or similar payloads and had similar goals to the Kaguya Selene mission. And it was doing essentially two big missions. One was to look at the lunar surface and to get good images and good altimetry. And the second was to collect remote sensing data on the composition of the surface as well. Chang'e 2 was similar to Chang'e 1, but it was primarily directed toward looking at the landing site for the Chang'e lander. So it was essentially a reconnaissance mission for a very specific spot on the lunar surface. Once it completed its mission, it left lunar orbit and went to the Earth Lagrange point 2, and then went from there on an asteroid expedition. So it was an extremely capable spacecraft, and it is still flying. Chandrayaan was a mission that was flown by the Indian Space Agency, but included payloads not only from the Indian Space Agency, but from the United Kingdom, from ESA, and from the United States as well. Again, collecting more and more detailed information about the lunar surface, similar in a way to the other satellites. Now, the first one that I think is really critical from the United States is something called GRAIL, Gravity Recovery and Interior Laboratory Mission. GRAIL was a spacecraft, or actually a pair of spacecraft, whose mission was to map out the lunar gravity field in incredible detail. And the idea behind this spacecraft was that the two co-orbiting spacecraft could determine the difference between themselves to an accuracy of about 1 micron. As that distance between the two spacecraft changed, that indicated that there was a change in the gravity field felt at orbit. And that in turn allowed us to do an incredibly detailed gravity map of the moon. Once it got its primary mission done at a particularly high altitude, they stepped the orbit down and got increasingly detailed data at lower and lower altitudes until, in fact, the spacecraft ran into the surface. Because the moon's gravity field is unusual, it's lumpy, we tend not to fly spacecraft close to the moon early on in a mission because it's very easy to have the spacecraft impact. So many spacecraft will be flown at a higher altitude initially and then flown lower once we have a good data set. Another specific mission flown by the United States was a spacecraft called LADEE. Several times in the course of the Apollo program, we thought we may have seen particulate materials high in lunar orbit, and that remained a mystery as to what actually the high altitude environment was, particularly with respect to lunar dust. And the LADEE mission was flown to essentially look for lunar dust and to understand the nature of that high altitude environment. Lastly, and perhaps the most successful of all the missions, is the Lunar Reconnaissance Orbiter. Lunar Reconnaissance Orbiter was flown initially in the Constellation program, and essentially what it was doing was collecting all the data we felt we needed to plug holes in both the lunar map and our concept of global variations in things like topography and composition. LRO was originally planned to be a 1 to 2 mission. It is still in orbit. It's been there for 8 years, and it has returned some of the most phenomenally accurate and detailed photographs of the lunar surface that have ever been recovered. and they have changed many of the ways we think about the lunar surface. The only lander that has been on the surface since Apollo is the Chinese U-2 lander, which was carried to the surface as part of the Chang'e 3 spacecraft. It landed in Mare Imbrium, about 40 kilometers southwest from a crater called Laplace F, and it operated for approximately 2 lunar days on the surface. It was really important because it deployed to an area we did not go on Apollo, and in addition to that, it deployed instruments that we simply didn't even have during Apollo, such as a ground-penetrating radar. And it has returned data that is revolutionary, and it was a magnificent mission. So I want to talk about some gross properties of the moon, and it's always important to start with what the moon looks like, both from the Earth and that part which we mostly cannot see, and that's the lunar far side. The moon has presented a variable face to humankind. Specifically, it's got dark and light areas. And the variations in albedo, the reflected light, whether they're bright or dark, it turns out tell us some very important things about the moon that we now know because of the various spacecraft that have been there. This is a series of lunar globes that look at 3 different elements: thorium, titanium, and iron. And I want to look at these in great detail, but one of the things I need everybody to recognize from this is that the albedo, the change in the gray tone of the lunar surface, actually maps very nicely to composition. This is the iron map of a goodly portion of the moon, and the variations range from brighter, warmer colors as higher iron and cooler, darker colors as less iron. Now, if you look at the moon in plain light, like we see the moon when we look up at it, you can see that the higher, brighter colors on the iron map correspond to the darker areas on the moon. And that's because the darker areas on the moon are filled with lava flows, and lavas are basaltic in composition, the same kind of rocks you see in Hawaii, and they tend to be higher in iron than the lighter color rocks on the rest of the moon. So we can see from that composition reflects albedo. Now, if we look at the titanium map, we see something very similar, although there are some variations in this. Not all basalts are alike. Some basalts have higher titanium, some basalts have lower titanium. The color scheme is the same as the iron map. Brighter colors have higher, lower colors have lower titanium. And you can see that not all the dark areas of the moon, the lavas, have the same titanium composition. We essentially discovered that from Apollo, from return samples. And we were lucky before we even knew this that we picked sites that coincidentally turned out to be places that had variations in titanium. But again, you can see on the western side of the moon and on sort of the central eastern side, we have a lot of titanium. In much of the rest of the moon, we don't have much titanium. Lastly, if we look at thorium, we see again the darker areas of the moon having a lot of thorium, and thorium is a radioactive element, and it's indicative of sort of evolved magmas that have spent a lot more time cooking, and that will be discussed in a later lecture. But again, if you go back to the picture of the moon that we see from the Earth, you can see that the concentrations of thorium match many of the colors that we also see on the lunar surface. In this case, they map to some place that we call the Procellarum creep terrain, where creep, K-R-E-E-P, stands for potassium, rare earth elements, and phosphorus. Let's talk about the lunar surface environment, and there's really 4 parameters that I think are really important. One is temperature and sunlight. The 2 are paired, and the other 2 are hydrogen content and what you can see of the Earth and how easy it is to communicate. The temperature on the moon really divides the moon into 2 different regimes. One is polar, which are colder, just like the Earth, and the other is the nonpolar environments, where, depending on where the sun is, it'd be hot or cold, just like the Earth. At noon, we get the hottest temperatures. On the moon, at noon, we get the hottest temperatures. When the sun goes down on most of the moon, it gets quite cold at night. The poles, on the other hand, are colder, but the temperature is much more stable than it is on the rest of the moon. Let's talk a little bit about hydrogen content. Hydrogen is a really critical element for essentially living off the moon. You can combine it with oxygen to make water. You can use it as rocket fuel. So where the hydrogen is really important. The nonpolar portions of the moon, the hydrogen ranges from as low as 10 parts per million to as many as 90 parts per million. The poles, however, we're pretty sure that the hydrogen content on average is greater than 150 parts per million, and it's why the poles remain an attractive target for lunar settlement. Lastly, direct-to-Earth communications. The moon is in locked rotation with the Earth, and that means that basically wherever you are in the lunar near side, the Earth will be in sight and it'll always stay in the same place. At the poles, the Earth is really low to the horizon. If the terrain isn't in the way, you can see it all the time, much as you do from the front side. But there are many times when the terrain may block it. The lunar far side never sees the Earth. So if you're going to operate on the lunar far side and you want to talk to the Earth, you're going to need a continuous relay satellite. So let's talk in more detail about thermal conditions, because the temperature is what we're going to have to work in when we're on the lunar surface. Nighttime surfaces are very cold, down to as cold as 150 degrees centigrade. And noontime temperatures are equally high, about 100 degrees centigrade. Polar areas are either always dark or have grazing solar incidence. So there are areas that we refer to as the permanently shadowed areas. These areas are extremely cold. In fact, many people have estimated that these are the coldest places in the solar system. The permanently shadowed areas on the moon never see the sun and probably have not seen the sun for hundreds of millions of years. Consequently, they are extremely cold, down to 50 to 70 degrees Kelvin. Another critical part of the lunar environment is micrometeorites. First, there's no atmosphere to impede the impact of all debris, so the speed at which, or the velocity at which it's coming in from space around the moon is not attenuated at all as it is on the Earth. There's a variable flux. I'm not going to repeat all the numbers on the graph there, but basically the smaller the object, the more there are of them. A lot of surface rocks have craters that are on the order of 1 to 10 microns. That's the size of the crater. In many cases, the damage from the impact extends far away from that actual crater, and it creates something we call zap pits. The Apollo astronauts noticed zap pits on the surface rocks, and once the rocks were back, it turns out that it becomes a very useful piece of data as to how long a rock's been sitting on the lunar surface and whether it's been tumbled. In other words, does it have the same face always facing the sky, or has it been rolled around? If it hasn't been tumbled, the top surface will have a lot of zap pits, the undersurface won't. If it's been tumbled around, the undersurface will have zap pits. And it turned out we could actually determine how rocks were bouncing around on the lunar surface by looking at the zap pits. One critical part of the discussion of micrometeorites is that even though there's micrometeorites coming into the moon and they're not slowed down, the impact hazard on the lunar surface is estimated to be about 4 times less than in low Earth orbit. So the lunar surface environment is much safer in terms of micrometeorites than low Earth orbit, where International Space Station is. Now, the moon's orbit is pretty interesting. Like all bodies in the solar system, it's not in a circular orbit, it's in an elliptical orbit. And in this case, the perigee and apogee being the farthest it's away from the Earth and the perigee being the closest it is, vary by about 45,000 kilometers. One key part of the fact that the moon has an apogee and perigee is that the size of the moon is actually quite a bit different when it's as far away as it can get and as close as it can get. The one on the left is when the moon is as far away as it is from the Earth. The one on the right is its closest approach. And there is a considerable difference in the moon size. So when you step out at night and look at a full moon and you think, gosh, that's a lot larger than I remember it being, sometime in the past. It's not an optical illusion. That's actually happening, and it's because the moon is in an elliptical orbit. There's something we call the barycenter, and that is the center, the point at which the entire system rotates, and that's about 1,700 kilometers below the Earth's surface. It is not at the center of the Earth because the moon is actually quite heavy relative to the Earth, so that center of rotation is actually displaced from the center of the Earth. The moon has an orbital period of about a month. We know this because every month we go through a new moon and we go through a full moon and then back to a new moon. It is not exactly a month long, so there are months that come along where you get 2 full moons in the month, and that's why. Okay, let's talk a little bit about the moon's orbit and eclipses. They could be more common if all of the orbital parameters of the Earth and moon lined up. Basically, what happens to get an eclipse is that at the point of new moon, in other words, when the moon is located between the Earth and the sun, it's directly on what we call the Earth-Sun line. That is the line that's drawn essentially between the center of the Earth and the center of the moon. Because the moon's orbital plane is different from the Earth, and because that plane precesses around the Earth because of tidal and gravitational forces, those 3 conditions, Earth-Sun line and the moon right in that Earth-Sun line, don't happen very often. And so it's a special case of a new moon. If all of those were aligned every month, we'd have an eclipse, but we're not so lucky. Let's talk a little bit about something we call libration. The moon wobbles around its axis, and it actually has what we call longitudinal and latitudinal axis. Longitudinal libration means it's basically wobbling back and forth on its elliptical plane. Latitudinal means it's wobbling back and forth on its essentially north-south line. Because of that, we can actually see slightly into the far side and the poles of the moon if we didn't have libration. So about 8 degrees beyond the 90-degree west and 90-degree east points, and about 6.5 degrees beyond the north and south polar. If you look at these 2 photographs that were taken at different parts in the year, on the left photograph, there's the crater Endymion pointed out, and you can't quite see it, but Mare Crisium is the black crater essentially at the center. If you look at the picture on the right, Endymion has now shifted to the left and more into view, and Mare Humboldtium, which normally we would not see, we can see. Likewise, Mare Crisium is no longer right on the limb, but is slightly tilted toward the Earth, and that's just libration at work. Topography is an important thing that geologists think about in terms of a planet's history and its conditions, because it tells us a lot about how strong the crust is and what's happening on the interior. We now have a really, really good idea of what the topography of the moon is like. The moon is bumpy. It has extremes in elevation from as low as 9 kilometers below an established altitude and as high as 8 kilometers above that. Now, we have pictures like this, and we use blue, cooler colors as the lower, and yellow, red, and white as the higher altitudes. But one of the things that's really key is that the moon has elevations extremes that are essentially the same as the Earth, from the seafloor to the mountains. There's a couple of things that I think are important to talk about. One is, of course, the lunar near side has the traditional thing we think of as the man in the moon patches of dark, but it turns out, of course, these are also where the moon is low, and that's consistent. Lava flows, when they erupt, flow into lower spots, and we know now that those lower spots are the remnants of very large impact craters from the early on in the lunar history. The lighter areas are what we call the highlands, in between the lower spots, and they're much elevated. Interestingly, if you look at the far side, on the lower part of the far side, we see this big dark blue area, and that's something called the South Pole Aitken Basin. That's generally acknowledged to be the largest impact crater in the solar system, and it's actually a pretty big hole on the moon, and we really didn't understand that it was there, although there were hints, until we had these kinds of maps more recently. In addition to the South Pole Aitken Basin, you can see at the equatorial part of the far side of the moon, we have our highest topography, again up to about 8 kilometers above the agreed on datum. The topography of the moon is largely bimodal. In other words, you're either on the rough, lighter colored highland areas or the smooth, darker colored Maria. When we consider roughness, we're really talking in most cases about whether it's mountainous or not mountainous, and those are big scale things in terms of the terrain. But it's also important to consider whether we have roughness at a human scale, or in the case of going back to the moon, on a lander scale. And the highland areas turn out to be actually smoother at a lander scale, and the Maria are rougher at the lander scale. Lunar landforms are dominated by cratering. We talk a little bit about lava flows, but even the lava flows are affected by cratering because the lava flows are found filling craters. There are literally thousands of impact craters, ranging from the size of the South Pole Aitken Basin, which is 2,500 kilometers across, to the zap hits, which are microns across. The shape and form of an individual crater changes as a result of two things. One is the size. The larger craters tend to be flatter floored. The smaller ones tend to be more bowl-shaped. In addition to that, as a crater spends time at the lunar surface, in other words, it goes from being a young crater to an older crater, it gets more and more subdued until finally it's just barely there. Unlike the Earth, the terrain on the moon is not dominated by plate tectonics process. It is solely a function of where things have impacted and the volcanic events that have filled those areas. In any event, completely smooth, flat areas on the moon are rare. They occur in the Maria, but the Maria are fairly old, so they have been broken by numerous craters as well. The slopes in the Maria are around 4 to 5 degrees on average, so it's not very, very steep terrain, although as you can see the crater in the center of this picture, if you get close to a young crater, the terrain gets quite a bit steeper. The Highland Maria boundary is generally sharp and abrupt, much as we see here at the Apollo 15 site in the Hadley-Apennine region. Because of that abruptness of the boundaries is again why we see the dark Maria areas. If those boundaries were not abrupt, the Maria would not have that sharp, obvious image on the moon surface. The highland terrain consists largely of rolling hills, some of them quite high, but nevertheless not jagged, steep cliff faces like we see on terrestrial topographies. The highland terrains are created largely by overlapping ejecta blankets from large craters. If we get close to a young crater, for instance like Tycho, the terrain is quite rough. But away from the young impact craters, the average slopes are 7 to 10 degrees, but the scale of the topography at, let's say, a lander image or a lander footprint is quite smooth. Surface lighting is something that not only we dealt with on Apollo, both in terms of operating on the lunar surface, but also seeing the topography for crews to land at, but also we'll be worried about it when we go back to the moon because we're there to stay. Apollo 12 had the shallowest sun angles, so 7.5 to 9.5 degrees, very shallow. Apollo 16 had the highest sun angles, 45 to 48 degrees. On the left is an Apollo 12 picture on EVA-1. You can see how long the shadow of the lunar module and the astronaut is. On the right is the Apollo 16 site at the highest sun angle. And in contrast, the surface is much brighter, the shadows are smaller, and in general, it's harder to see your way around on the terrain in high sun angles than it is in lower sun angles. Anybody that's ever been skiing in flat light knows that you can ski off some remarkable terrain that you didn't even see because the shadows aren't there. In some ways, driving around on the moon in high sun angles is going to be similar to that, and possibly when you drive, you're going to have to be tacking back and forth down sun. These are two pictures essentially looking up sun and down sun. Apollo 12 EVA-1 down sun. The sun is 7.5 degrees, so you can see if you're looking directly down sun, you don't see much, but if you look to the right or to the left, you can see quite a bit. And that's what I mean about having to tack back and forth around the sun. If you want to make sure you don't drive into something that's exciting, you're going to have to be careful how you drive. In contrast, Apollo 17 EVA, sun's about 16 degrees, and that's looking up sun. The terrain is somewhat easier to see, but it's still glaring sunlight when you're going directly into the sun. A unique aspect of working on the lunar near side in the dark is illumination by Earthshine. Because the moon's orbit is locked and we always see the same face of the moon, the Earth always stays in the same spot in the sky. And when you have a full Earth, it's something like 80 times brighter than a full moon. At essentially lunar midnight, if you're out working under the Earth with a full Earth, it's as bright as about 8 o'clock on a summer evening on the Earth. So the reality is that when you're out at night in Earthshine, you'll be able to see just about everything you need to without artificial illumination. John Young once told me that not only was it bright enough to see the lunar surface from orbit with Earthshine, you could actually tell color differences and see individual craters with Earthshine. So Earthshine is going to be an asset that's really important for future lunar operations, unless, of course, you're on the far side. The far side, the Earth is never in view. So when the sun goes down on the far side, with the exception of starlight, it's going to be really dark. In addition to that, when we're working at the poles, because the sun is so low to the horizon and the Earthshine is so low to the horizon, you're almost always going to need some level of illumination so you just don't step into dark holes because of the low sun angle. Let's talk about regolith. Regolith is one of those aspects of the lunar surface that has received a lot of discussion over the years. There will be a further lecture just on regolith, but I want to touch on it here to give you an idea of what it is. The basic definition of regolith, and this is a geologic definition, is the layer or mantle of loose, unconsolidated rock material of varied origin that rests on bedrock over most of the lunar surface. In other words, regolith is what happens if you take bedrock and just beat it up until it's just nothing but fragmental material. We use regolith on the Earth to talk about soils as well, but the moon is essentially just plain old rock. The regolith can be formed in place or it can be transported from adjacent locations. Generally speaking, if you pick up a handful of regolith at any one spot on the lunar surface, roughly 90% of the material in your hand is going to have been derived very locally. About 10% will have been transported in by meteorite impacts from other locations. There are a lot of processes that affect regolith formation. Obviously, the principal one that creates regolith is meteorite impact. It breaks up the bedrock into all sizes, and the variety and sizes of meteorites create variety and sizes of regolith. In addition to that, we have cosmic rays, we have solar wind, and those create variations in the regolith which have caused it to be quite different at a very, very small scale, and I'll leave that discussion to the subsequent lecture. The median particle size of regolith is about 40 to 130 microns. That's really small, and it's much smaller than we experience, for instance, when we're at the beach. 95% of the regolith is less than 1 millimeter, and if you're out the beach, the roughly average size of the sand is about 2 millimeters. So the moon is not going to be like a day at the beach. There are a lot of things in the regolith. There's a lot of things mixed up. It's ground broken rock, it's impact melt, it's bits and pieces of meteorites, so it's very variable. The graph shows the variation in the nature of the regolith at various landing sites, in this case, surveyor landing sites. You don't need to take away real detailed specifics on this, but it's important to recognize that the regolith isn't the same all around the moon. As the surface gets older, in other words, it's been exposed to the lunar, at the lunar surface for a longer period of time, it changes grain size, it changes character. So every landing site will be slightly different. When we landed the lunar modules on the regolith, we had a variety of essentially interactions between the regolith and the lunar module. First thing, of course, is everybody knows that down close to the surface, the astronauts saw dust moving around. And if you look at the upper left picture and the lower left picture, those are sort of striations, little ridges and troughs created in the regolith by the ejecta, by the exhaust from the lunar module. If you look at the upper right picture, you can see that in that case, the regolith was quite fluffy and the foot pad sank, probably 1 to 2 centimeters into the regolith. On the lower right picture, you can see that, in fact, the foot pad is just sitting on the regolith. So how compact and how fluffy the regolith varies from place to place. But none of it, in no place, is that fluffiness deeper than about 10 centimeters. There's been a lot of discussion about dust and what it does to astronauts and hardware and rovers and spacesuits and things like that. The picture is of Gene Cernan after EVA-3 on Apollo 17. He's just pulled his suit off, and you can see that he's got a lot of dirt on his face, not because the regolith came into the suit during his EVA, but because the suits, which you can see piled on the ascent engine cover in the background, were pretty dirty from walking around on the lunar surface. There's been a lot of discussion about levitated dust. There's been a lot of discussion about whether dust is a critical design issue that will cause failure if it's not followed or not paid attention to. Levitated dust has been suggested both by the glow, horizon glow taken on the Surveyor cameras, and by photographs and notes made by Gene Cernan as the Apollo 17 command module approached the Terminator. There's been a lot of discussion, is dust levitated? Does it move around on the lunar surface? There's a couple of things we can look at to try and get some idea of whether there is a large-scale transport of dust on the surface. The first is that Apollo 11, 14, and 15, we put laser retroreflectors on the surface. Now, these were corner cube reflectors that were designed to reflect laser light back to the Earth. So if there's dust moving around, you would really expect those corner cubes to get covered. And even if they're not completely covered, you would expect to see some reduction in the signal strength coming from the moon over time. The Apollo 11 retroreflector has been on the moon now for over 48 years. The others somewhat less time. There has been no evidence of any degradation in laser signal over the lifetime of these arrays. So if there's dust moving around, it's not covering the retroreflectors. When we went to the moon on Apollo 12, we landed near the Surveyor 3, which had spent 31 months on the lunar surface prior to the arrival of the Apollo 12 crew. Although there was some dust coating on parts, the patterns on the coating indicated that the dust was blown onto the Surveyor either by the lunar module landing or by the engines of the Surveyor itself. Again, there was no evidence of dust having settled on the spacecraft from any other source other than the engine exhaust. In fact, there was even a study published where a research team looked at the Surveyor parts brought back to the Earth, and they saw no evidence that dust was on these parts except by blown on by the engine bells. Now, when we establish an outpost, because engine bells do blow dust around, we're going to have to be careful about where we land our spacecraft so that we don't spray dust all over our habitats, deployed equipment, and instruments on the surface. So in that case, we will have to accommodate the fact that if you have an engine coming past the surface, it's going to blow dirt around. There's been some discussion also about whether dust is moving in the Terminator. When the Terminator comes by, there's some suggestion that there are variations in the electrical current, which some people have suggested would cause dust to levitate. So I want to talk a little bit about that particular issue as well. And this concern was raised before Apollo, and Apollo, I think, provides us some pretty conclusive proof that it's not happening. The first, I think, that's really important is that the albedo gradients between the highlands and the mare, the highland rocks being lighter colored, the mare rocks being darker colored, are sharp and distinct. They're preserved at remote sensing scales, they're preserved at photographic scales, and the crews on the surface could see them. In the upper right, the right is a picture of the Apollo 17 site. You can see very clearly that the highland terrains are distinct from the mare fill in the valley. At the left, you have a geologic map from a publication in 2002 that shows by using remote sensing data that those albedo variations indeed represent compositional variations, and that there is no sense that there's a homogenization of the lunar surface from dust. Likewise, if you go up to orbital altitudes and look at things like the Mare highland boundaries, in this case Mare Crisium, on the left you see the albedo picture, on the right you see the iron map, and again, you can see clearly that iron does not bleed over into the highland terrain, that the boundaries, the albedo boundaries, are as sharp in the remote sensing data as they are in the visible light. LADEE was a spacecraft I talked a little about earlier as having been sent to the moon recently to look at whether there was a dust component in the high altitude lunar exosphere. And in fact, LADEE saw, while there was some tenuous dust, there was no evidence of electrostatically lost dust at high altitudes. Lastly, if a lot of dust was moving around, we would expect the rocks at the surface to be either covered in dust or at least have a mantle of dust. And there is no evidence on rocks that have been essentially exposed to the surface for hundreds of millions of years of any accumulated dust blanket. We conclude that lateral dust transport on the moon, if it happens at all, is very inefficient and is not coating the lunar surface with new dust every time the sunrise goes by. Let's talk briefly about the origin of the moon. We'll get into more detail in subsequent lectures, but there were three traditional modes that were advanced prior to Apollo. Some of these modes date back to literally Charles Darwin's grandfather. The first was what we call the fission model. The idea was that early on in the history of the Earth, when it was largely molten, and if it was rotating fast, mass dissimilarities would cause a bulge to be created, and you would essentially birth a moon from that mass distinction. Darwin's grandfather actually suggested that the Pacific Ocean was where that body came from. The second origin theory was that both the Earth and the Moon essentially accreted in the same spot, but created two different bodies, what we call co-accretion. And lastly, we thought that potentially the Moon was formed elsewhere in the solar system and was ultimately captured by the Earth when the Moon in a different orbit came nearby. We know for sure that the moons of Mars, for instance, were captured in such a way that they're actually asteroids which were forced out of the asteroid belt and were captured by Mars and are now permanent satellites. So one of the outcomes of the Apollo program was we discovered that these models are, for the most part, wrong. And we did that on the basis of understanding that the Moon had undergone a fairly violent early history, and by inference the Earth, and also by looking at similarities and differences between lunar samples and terrestrial rocks. After quite a few years, and I mean like a decade, more than a decade after Apollo, that length of time was necessary to really assimilate all the data and start to come up with new models of the formation of the Moon. And what is now called the giant impact hypothesis is the reigning model for the creation of the Moon. What we believe now is that very early in the solar system's history, in some cases no more than 10 to 15 million
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
It's important to remember that when John Kennedy made the commitment to go to the moon in 1961, the United States had a sum total manned spaceflight experience of one person, Alan Shepard, for a 15-minute, 28-second suborbital flight. If you add in the Soviet experience, Yuri Gagarin had done essentially one 90-minute orbit. So when Kennedy threw down the gauntlet to go to the moon, the entire human spaceflight experience was essentially about 105 minutes. Kennedy's speech and his commitment was marvelous in its brevity and its simplicity. What he said was, go to the moon before the decade is out, bring somebody back safely to Earth, and probably is one of the reasons why we were so fired up and why it worked so well. One part I think that's really important to point out is that after Kennedy told us to go to the moon, a paragraph or so later in the speech, he said something that I think is also really important. He essentially said that he was asking the Congress and the country to accept a new course of action which would last for many years and carry very heavy costs. In his opinion, if we were to only go halfway or change our mind in the face of difficulty, he felt it would be better not to go at all. I think that is a watchword or an important concept that we need to keep in our minds whenever we do something big like Apollo. One of the best books on Apollo was Apollo: The Race to the Moon by Charles Murray and Catherine Cox. And they point out that Apollo was not a spacecraft, it was not an engineering project, it was not a means to improve science knowledge. In effect, John F. Kennedy pushed a heap of chips to the center of the table with the Soviet Union on the other side and said, call. In other words, he pushed us and the Russians to do more than just simply do simple suborbital or orbital flights. So, the big question is, how did we go from that one 15-minute flight to walking on the moon in less than 9 years? My personal bias is that the answer to that question has essentially 7 key points: national will, money, heavy lift launch vehicles, landers, spacesuits, the operations practices that allowed us to manage human spaceflight, and luck. The first 6 are obviously things we have under our control. However, luck is not, but you should never make a mistake by thinking we weren't lucky on Apollo. We were incredibly lucky on Apollo, and the few mistakes we made showed us the way to not make that mistake again. In fact, it's really important to recognize that when Apollo 18, 19, and 20 were canceled, at a high management level, at some level, there was a certain amount of sigh of relief because management felt like we'd been lucky and we didn't want to push our luck too much. Let's talk about these individually. National will, I think, is the first and most important part of this. The folks that took us to Apollo at a management level and the younger people were people that had history in World War II. They understood that a combination of real solid industrial production and commitment was really important. The generation that went to the moon on Apollo was not only used to succeeding, it understood a commitment to a large long-term goal. The country felt that Apollo had a similar kind of commitment as World War II, and it fired up the nation like nothing before. And certainly nothing in some ways has fired it up since. I think the second key issue of Apollo was money. Apollo had financial resources that we can only dream about in the space program today, or for that matter, most programs. In 1961, at the time of Kennedy's commitment, the NASA budget was just shy of $1 billion, and Apollo received about 10% of that. At the peak of Apollo spending in 1966, the NASA budget was $4.5 billion, and Apollo received just shy of $3 billion. The NASA budget at that time was something like 4% of the federal budget. We receive less than 1% of the budget today. Heavy lift launch vehicles, and particularly the Saturn V, were another key part. The Saturn V remains the largest single launch vehicle successfully flown, either by the United States, the Russians, or any other program. The Saturn V was an incredibly complex 3 million part machine that essentially worked, with one exception, flawlessly through every one of its launches. Without the Saturn V, I don't think it would have been possible to do Apollo by the end of the decade. The other thing that's important about the Saturn V is that to build the Saturn V, we also had to build the infrastructure at the Cape to manage the vehicle, which included the VAB, the crawler, Launch Complex 39, all of the pad hardware, and the launch pad itself. And we still use that. It will be the mainstay of our manned space program for the foreseeable future. I think the fourth key part is landers. The fact is that building the lunar module was totally important in success on Apollo. Without the LEM, we couldn't have done the mission because it would have involved landing great big rockets on the moon, climbing way down to the lunar surface and taking those big rockets off the lunar surface. In any event, deciding to go lunar orbit rendezvous was just the start of the fun, not the end, and the lunar module was probably, prior to the Space Shuttle Orbiter, probably the most complex spacecraft that had ever been built. The lunar module was the first true spacecraft in the sense that it could only operate in a vacuum. It had no thermal protection system, so it couldn't successfully re-enter the Earth's atmosphere. One of the interesting things about the LEM design was because we didn't really know how hard it was going to be to land on the moon, Grumman built into the LEM a considerable thrust margin, probably more than was really justified for a simple flags and footprints mission. Consequently, when we went to later missions and built a Block 2 LEM, the LEM's payload capacity was sufficient to put on rovers, big science packages, consumables for 3 days on the lunar surface, and we even flew a telescope to the moon at one point. The fifth key part, I believe, is EVA systems. A good example of how far we came is during Gemini 9 in June 1966, Gene Cernan did an EVA in a modified, essentially Air Force pressure garment that was so hard to work on that he was unable to successfully complete the EVA. He was beat up physically. His visor was so fogged that he had to use his nose to wipe a spot to see through to get back to the hatch of the spacecraft. The suit was so immobile that his EVA was essentially potentially life-threatening. In 1972, essentially 6.5 years later, Gene Cernan again went EVA, this time on the lunar surface. He did 3 successive EVAs over 3 days and had nary a qualm. He compiled over 21 hours of solid field geology experience on the lunar surface, and he set a record which has not been broken. In less than the 6 years that it took to go from essentially Gemini to the first Apollo mission, the EVA system technology had improved to the point where EVAs became routine, and we're still building and using that EVA capability on Space Station. The success was a combination of, like all of this, a lot of hard work, good engineering, and a lot of experimentation. By the time we finished with Apollo, we had built over a dozen different spacesuits before we down-selected to what became known as the A7L and the A7LB spacesuits. In addition to that, we built a portable life support system, which was probably one of the most complex small pieces of hardware ever built. It went through 25 EVAs, both in Earth orbit and on the lunar surface, without a single major malfunction. A lot of people whose names we're very familiar with, like Christopher Kraft and Gene Kranz, invented the operations practice that enabled us to go to the moon. They literally made this up as they went. Nobody had ever done this before. If you've seen the movie Apollo 13 or spent any time looking at Apollo, everybody knows that the flight control teams, both in the front room and the back rooms, were critical to getting success on Apollo. But in addition to that, they developed the training techniques, the flight dynamics techniques, and everything that not only allowed us to successfully do the Apollo 11, but allowed us to successfully build on each successive missions to do all of the exploration we did on the lunar surface. One of the things that I think is really important is how flexible we actually were during Apollo. We tend to think of the Apollo missions all ran by a very tightly scripted flight plan, and nothing ever changed from Apollo 11 to Apollo 17. But on Apollo 11 and Apollo 12, when we went down to the lunar surface, the lunar module started from a 100-kilometer orbit, performed essentially a burn that took it down to 10 kilometers, and then from that low point did the powered descent into the lunar surface. Consequently, you use the LEM engine to essentially do the whole lunar landing. After Apollo 12, they realized that the command and service module had more than enough delta V, and from Apollo 14 on, for every lunar landing, the command service module did what was called the descent orbit insertion burn. That basically left the LEM with its full complement of delta V from the time it started down to the lunar surface from 10 kilometers. That margin enabled us to put on things like rovers, extra consumables, and led to the incredible success of Apollos 15, 16, and 17. And it was all because we were willing to stop as the program was going on and say, hey, there may be a better way of doing this. So the question is, what did we actually do on the moon? The Apollo program landed at 6 different locations on the lunar surface, starting with Apollo 11 and building through Apollo 17. Apollo 11 was essentially the final engineering mission that followed in the wake of Apollos 7 through 10. If you look at the mission of each of 7 through 11, they all had specific engineering boxes they had to check, such that the Apollo 11 crew could get down to the lunar surface. The Apollo 11 mission, in a sense, was the fulfillment of Kennedy's commitment: land men on the moon and return them safely to the Earth. But in addition, it had the objectives to prove out the EVA system, return the first science from the lunar surface in the form of a small set of deployed science instruments, and bring back a modest collection of lunar samples. The Apollo 11 landing was a cliffhanger, even beyond the fact that it was the first lunar landing. And a number of problems came up and had to be solved in real time. The first one was what was called the 1201 alarms, the computer saturation alarms, that came up in the final portion of the descent. It sent caution and warning alarms that were not ultimately serious, but nevertheless caught everybody's attention. Luckily, in a number of simulations prior to the Apollo 11 landing, these alarms had also come up. And one flight controller in particular, Steve Bales, went back, figured out what the nature of the alarms were, and so he could tell Gene Kranz that we could safely proceed and ignore the alarms. The second problem was that there were a combination of navigational errors that led to the vehicle essentially targeting long and heading outside of the pre-planned landing ellipse. The reasons were numerous, ranging from simple things like uncommanded thruster firings and essentially starting down slightly late, things like that. The bottom line, though, is when the crew pitched over, it was clear they were not going to be able to land exactly at the spot that they wanted to land. The third problem was that as the crew approached the designated landing spot, it was clear that the LEM was headed for a boulder field that was not appropriate to land at. And although Neil Armstrong essentially took a good look at the site and thought maybe if we land short, we can get close to big boulders that might be interesting scientifically, prudence took over and he proceeded downstream and landed at a more satisfactory landing area. The last problem, which was something that turned out to be an interesting problem throughout the Apollo program, was as the LEM went into its final descent from about 30 meters, the descent engine thrust sent out clouds of dust, which made landing, essentially the view of the landing site, obscured, not seriously, but enough that the crew really couldn't exactly see the ground that they were landing on. I think the really key lessons we learned from Apollo 11, which is something we keep learning, is that we need pilots flying the spacecraft. The fact is that if Apollo 11 had essentially been flying on an autopilot that the crew could not override, they would have either crashed or they would have had to abort. The second key lesson was that the lunar surface was covered up with a loose ground-up rock layer that was compacted below about 10 centimeters, but loose and fluffy on the surface. And that proved to be a bane both a bane and a blessing throughout the entire Apollo program. The third is that smart, well-motivated, and well-trained crew members greatly improved the science return. A good example of it is that Neil Armstrong realized at the end of their EVA that there would be a lot of empty space in the rock box. And rather than come back with empty space, he basically took the shovel and filled that empty space up with scooped up soil, which became one of the key soil samples, not only of Apollo 11, but of the whole lunar program. And largely on Neil's initiative, the crew walked about 100 meters west of the landing point to get a picture of Little West Crater, which proved to be the first photographic evidence we had of lunar bedrock and the depth of that regolith layer. We jump forward to Apollo 12. Apollo 12 was our first step toward doing real science on the moon, but it was still an engineering flight. Apollo 11 proved we could land on the moon, but because of the various navigational errors, it landed outside of its landing ellipse, and in fact, for a while, we weren't even sure exactly where Apollo 11 landed. Apollo 12 had the objective of landing at a pinpoint spot. The question was, if we say we want to land at spot X, how close can we put the LEM down to that spot? In order to do that, they decided they needed an interesting target, and they decided that they would land within walking distance of the Surveyor 3 spacecraft, which had landed on the moon in April of 1967. In addition to that task, the crew would deploy the first ALSEP, or Apollo Lunar Scientific Experiments package, an array of science monitoring equipment that had a lifetime of about 3 years. Okay, so Apollo 12, I think it surprised everybody, perhaps even the crew, by making precision landing possible. In this case, they put the LEM down only 13 meters from their planned landing spot. That's less than 40 feet. That enabled the crew in the course of 2 EVAs to walk around and the lunar surface and get to the Surveyor spacecraft and bring parts back, proving essentially our first long-duration exposure facility. The ALSEP package proved their worth, although the deployment was time-consuming and it really took up one whole EVA. And then it proved that walking traverses in excess of 2 kilometers can be accomplished safely and easily by the crew members. Apollo 13, of course, everybody knows about, and it was a successful failure. The Apollo 13 mission landing point was considered to be sufficiently important that Apollo 14 was subsequently targeted to go to the same landing spot. The Apollo 14 landing mission was the first physically challenging landing site that we had. In other words, it was not flat Maria. I guess the best way I can explain this is the difference between trying to land in, let's say, Iowa and landing in the Appalachian foothills. And the EVAs that were planned were also considerably challenging. In addition to putting out another ALSEP package, the crew had a pull cart called the Modularized Equipment Transporter that was dubbed Shepard's Rickshaw that they would take on what was to become the most physically challenging EVA that was ever completed on Apollo. The plan was to climb up the rim of Cone Crater. Cone Crater was an approximately 300-meter wide crater that had punched through an important rock layer on the lunar surface that hopefully would allow us to date one of the most important early impact events in lunar history. The second key science point was that the site was overlain by material that appeared to have been ejected by Copernicus Crater, which is one of the youngest large craters on the lunar surface. Assuming we could bring back samples of those 2 events, we could really sort of narrow in on the chronology of impact events that occurred on the lunar surface. Apollo 14 proved to have a number of serious challenges that unfortunately compromised science return. The most difficult of this was navigation and dealing with the terrain. The landing area, as I said, was hilly, and it was sufficiently steep that climbing those hills in the A7L pressure garment was very difficult, and pulling the modularized equipment transporter essentially proved to be impossible. The second thing is the nature of the topography and the fact that they were, in some cases, outside of the site of the LEM made navigation very difficult. The reality is that when you're on the lunar surface, there's nothing that gives you a sense of how far the horizon is, how big things are in the distance. We don't have any telephone poles, we don't have cars, we don't have trees, the things that we use on the Earth to give us a sense of how far away it is to someplace. And the lack of those things made navigation on the lunar surface very difficult. After Apollo 14, the program sort of stepped back and started considering what to do with the remaining Apollo missions. And it was decided that the Apollo 15, 16, and 17 missions were no longer to be, in effect, engineering flights, but they were going to go to high-value science targets, spend a long time on the surface, and essentially do real solid exploration of the lunar surface that had not been effective or not been possible on the first three missions. The Apollo 15 to 17 mission went to the moon with enough consumables for a 3-day stay, and more critically, a vehicle, a car, they'll call the Lunar Roving Vehicle, that enabled the crew members to essentially climb on and drive off to the sites they wanted to visit scientifically rather than walk. Now, a lot of people have this vision that the Lunar Roving Vehicle went zooming along the lunar surface, and the fact is the Lunar Roving Vehicle did not go terribly fast. In many cases, it didn't go really faster than walking. The key part of using the Lunar Roving Vehicle was because the crew members were sitting down, their metabolic rates and their use of the oxygen in the portable life support system was sufficiently slow that essentially they extended the gas tank of the Bliss. Consequently, instead of doing EVAs that were on the order of 4 hours, using the LRV, now you can get 7 or 8 hours on the lunar surface and cover far more territory than you could go if you had to walk. Apollo 15 landed on a Mare surface, essentially a flat surface, but it was located between a very considerable range of mountains called the Apennine Mountains and along the edge of a rift in the lunar surface called Hadley Rill. The mission objectives were to explore both the rill and the highland terrain, to sample lunar highland rocks in place to determine what the composition of the lunar highlands were and hopefully bring back some of the earliest pieces of the lunar crust possible. And then to sample and photograph the rill to understand how lunar rills are formed and what essentially they're telling us about the lunar surface. In addition to those objectives, the Apollo 15 mission included an enhanced ALSEP array, which had a heat flow experiment, which would require drilling holes 3 meters into the lunar regolith. Not only would it give us an understanding of the heat flow from the lunar interior, but it would also give us the deepest regolith core that we would ever get on Apollo. So Apollo 15 was a tremendously successful mission. I think the first and foremost thing that the Apollo 15 crew was to bring back a sample which became known as Apollo Sample 15415, or the Genesis rock. This was a sample of the primordial lunar crust that was almost 4.2 billion years old. If you want to think of that in terms of, the entire history of the universe, that rock is literally represents 1/3 of the entire age of the universe, and it is in fact one of the oldest rocks we've ever had our hands on. In addition to that, photo documentation of the wall of Hadley Rill enabled us to understand how lunar lava flows were erupted and changed and improved our understanding of lunar geologic processes throughout the whole history of the moon. In addition to that, the Lunar Roving Vehicle proved its worth. It took crews up slopes in excess of 20 degrees and at distances far beyond where the crews had walked on Apollo 11, 12, and 14, went out to, in fact, 5 kilometers. The Apollo drill proved to be somewhat problematic, particularly in extracting the core out of the lunar surface. It became so difficult that, in effect, it ended up having Dave Scott bang up his shoulder and screw up his fingers, and between the physical exertion, Jim Irwin was later found to have had some cardiac irregularities, which proved to be a minor heart attack on the lunar surface. The timeline and ground supervision at times proved to be problematic in light of what the crew was seeing in the field, which led to the understanding that when the crew's on the ground in the field, they are in effect the experts. Apollo 16 was the first and only, in effect, pure highland site that we visited on Apollo. When you look up at the moon on a given evening, you'll see the dark areas and the light areas. The light areas are what we call the highlands, and Apollo 16 was the only flight that essentially landed on a pure highland site. The mission objective was to collect geologic observations on a number of highland landforms, which were thought to represent volcanoes in the lunar highlands, as well as set up another ALSEP array. The mission was notable for a number of reasons. The first is that poor photography from previous missions meant that we really didn't have a good understanding of what the landing site topography was going to look like. In fact, the smallest thing we saw at the Apollo 16 site prior to the mission itself was about 20 meters in diameter. So the bottom line was that it was a pure flying job from pitch over to landing. And the reality is when the crew pitched over, they were seeing the landing site for the first time. In addition, the site geology turned out to be different from what the scientists had thought it would be before the mission. And consequently, a lot of the mission plans went out the window. However, the quality of the geologic training that the crew had enabled them to just basically take over and do a field investigation, just like they hadn't ever had any training on what they thought they were going to find on the lunar surface. The Apollo 16 results made it another extremely successful missioning. It did point out that the best scientific reasoning can lead to the wrong conclusion, particularly when you're going someplace that nobody's ever been before. And what you have to do is learn to fall back on your training and move forward, regardless of what you thought you'd see in the first place. The samples indicated that the lunar highlands were geologically extremely messy. They were dominated by large impacts, and there was no evidence of lunar volcanism, contrary to what we thought we'd see before we went on the mission. The mission also showed that having crew members that had an extensive geologic training gave us the confidence to move forward without having to essentially have the ground drive the crew as if they were carbon-based robots. And the Apollo 16 crew did a fantastic job in spite of the fact that they were seeing something they didn't expect to see. Although the highlands turned out to be not as nasty a place to land and drive as we thought it might be, the fact is that young impact craters that we saw proved to be very difficult to work around. They're very rocky. You couldn't get terribly close to a very young impact crater with the lunar roving vehicle, and the interiors were very steep, and any thoughts we had of going down into the craters were not realized. There were some problems in the mission. There were some malfunctions with the ALSEP, partly because of the fact that the crew's equipment got hooked in some of the cables. In addition to that, the mission had to land about 2 orbits late. That led to a truncation of the third EVA and caused the science backroom to engage in a drastic replanning effort before the crew went out on their third EVA. Apollo 17 in many ways was the culmination of the Apollo exploration of the moon. It landed on perhaps the most challenging landing site, a Mare valley called the Taurus Littrow Valley in Mare Serenitatis. The valley was between 2 very high massifs, well over 3,000 meters tall. And initially, it was difficult, in fact, to fit the landing ellipse into the landing site. The mission was also noteworthy that that the lunar module pilot, Harrison Schmitt, was the first geologist to fly in space, and it made for a different crew dynamic. During the landing, Harrison Schmitt was clearly Gene Cernan's co-pilot, but once on the surface, Schmitt took over as the lead scientist, and Cernan was his essentially backup field assistant. The mission was also noteworthy in that the crew traveled farthest from the lunar module, almost 10 kilometers, and drove up the steepest slopes, 26 degrees, of any Apollo mission. The Apollo 17 had probably the best science return of any Apollo mission. This was affected largely by the fact that you had a geologist on the crew, but you also had a commander on the crew who had his own set of observational skills and high-quality geologic training. And the dynamic between the two of them led to very impressive geologic observations. The landing site also cooperated in that it provided the best access to rocks that could be tied through things like boulder tracks to bedrock units exposed on the upper reaches of the adjacent massifs. In addition to that, we had the unprecedented find of orange soil at Station 4, which turned out to be an example of a lunar volcanic eruption. In addition, there were a number of new geologic tools which allowed more samples to be collected with very minimal hits to the timeline by simply scooping dirt off the lunar roving vehicle while you're driving around. There were a few operational glitches, as on Apollo 15, the lunar roving vehicle fender failed, and that ended up showering both the crew members and the lunar roving vehicle with dirt from the lunar surface. However, the ground got together and basically built through photographs, clamps, and good old-fashioned duct tape a new fender which proved its value. So I want to talk a little bit about why Apollo matters. You know, we look back on Apollo with a certain amount of nostalgia, but we don't always think about why Apollo was so important. The first critical thing about Apollo was it taught us that the moon is not simply a big dust ball collected up from the remnants of the solar system formation. Prior to Apollo, we thought that the moon was essentially a big dust ball and that processes both on the moon and by implication the Earth were essentially through most of geologic history quiescent. The reality is we discovered that from the Apollo samples that the formation of the moon was incredibly violent, involving massive impacts and essentially melting of the moon itself down to several hundred kilometers, something that prior to Apollo wasn't even considered possible. And in addition, the implication was if it happened to the moon, it happened to Earth. Essentially, as we have gone through the solar system with spacecraft since Apollo, Mars to the outer planet satellites to even places like Mercury and Venus, it has showed us that the history of the moon is the history of the solar system. So in large part, it's not too far to say that our entire understanding of the history of the solar system and the processes extant has completely changed as a result of the Apollo samples. The second critical part about Apollo that I think really matters is that we learned how to build robust spacecraft that could successfully complete a nominal mission and also could respond to contingencies in a way to bring their crews home safely. Apollo spacecraft had few single-point failures and dead ends that would affect negatively crew survival and mission accomplishment. Apollo 13 has often been described as a successful failure in that the scenario was something that had never really been practiced and we had to make up as we went, but nevertheless successfully brought the crew home. The other accomplishments that I think are critical is the Apollo 12 landing within 13 meters of its designated point showed that you can land on planetary surfaces from orbit, and it's not just simply a matter of guessing where you land, that you could control a landing to a specific spot. In addition to that, the ability of the lunar module to accommodate an increase in lunar surface time and delivered mass to the surface was critical. The third reason why Apollo matters is that we learned how to do successful manned spaceflight. Prior to Apollo and the commitment to do Apollo, we really didn't know how to do what we do routinely now. The whole complement of forward control rooms, back rooms, mission support rooms, controllers, everything that we know now about how to do spaceflight grew out of Apollo. And without that, doing shuttle, doing space station would have been impossible. The fourth reason why Apollo matters is that we learned to build very large boosters, culminating in the Saturn V. The Saturn V could deliver to orbit the equivalent mass of the Atlas and Mercury spacecraft that we'd been flying to orbit only 6 years earlier. Without large boosters, shuttle would have never happened, we would have never built space station, and we certainly would have never done Apollo. The fifth reason why Apollo matters is that we learned how to do scientific exploration of a planetary surface with humans. This went from pressure garments that enabled the crew to get safely outside their spacecraft, portable life support systems that enable us to get well away from a landed spacecraft, rovers that could transport the crew to significant distances, up to almost 10 kilometers on Apollo 17 and potentially farther, and scientific instrument packages that could be installed on a surface and run reliably for years. So there is some sense in some scientific communities that I consider to be both ignorant and arrogant that little science was produced from Apollo. But as I alluded to earlier, nothing could be further from the truth. Everything we now know about the history of the solar system came from Apollo. And we got that information because we had crew members that could do the scientific investigation process. So there are a lot of lessons from Apollo for future exploration, but in my opinion, there's a number of really key ones. The first thing is that things break despite your best designs and plans. You should expect things that will break, train your crew members how to fix them, and fly your mission. The second is there's never enough time to do everything and see everything. So make a plan and stick to it. But don't get so hung up on the plan that when you find something new, like the orange soil on Apollo 17, you can't respond to it. The third thing is that the judgment of the crew on the surface is really better informed than the folks on the ground. And we should always listen to the people that are there when we're taking into account what's going on. The fourth thing is that navigation capability on the ground is a critical need. It's very easy not so much to get lost on the moon, but not really know how far you need to go and exactly the direction you need to go. And having navigational capability is critical. The fifth thing is that we need the proper tools and the proper procedures for the right situation. If you're taking a soil sample, you need to have the right tool to take a soil sample. Likewise, taking a rock sample. The sixth thing is you want to maximize crew flexibility. We send people to planets because their intellectual capabilities allow them to understand what's going on the fly. This is something robots can't do, and we need to always keep that in mind and maximize that flexibility. The seventh thing is when we have science station deploys, we should automate them as much as possible. Essentially, every Apollo crew who put the LSEP together grumble about how hard it was and that the fact that it took up a whole EVA. If we can automate that in the future, we should. However, anytime you automate something, go back to rule number one. Things break, and you should leave room for crew intervention, regardless of whether it's supposed to be automatically. The eighth thing is that you've got to keep your eyes open for unexpectedly useful things. A prime example is on Apollo 16, the crew executed right after landing something that was called the stand-up EVA, where Dave Scott opened the top hatch of the LEM and basically looked around from that high vantage point and developed his sense of what the landing site was like. That wasn't originally in the flight plan for 16. It was an idea Dave came up with, and it's the kind of thing we need to keep our eyes on. The last thing is that lunar dirt will be a pain, but it is not magical. It's not pixie dust. And there are solutions that can be found to mitigate its problems on the lunar surface when we go back, and we need to be constantly thinking of them. I'll finish this lecture by returning back to the quote from Charles Murray and Catherine Cox, that Kennedy's Apollo was a pile of chips pushed to the center of the table. The things that drove Apollo, the time spent, the innovation, the creativity, the pressure, all pushed back to that center goal that Kennedy put out there. And it led to us doing the best work I think this country has ever done. And we should keep that in mind when we go back to the moon.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
People often think that science took a back seat, and to some degree it had to the geopolitical aims. But still, it really got started very early. And indeed, for the last several missions, really beginning with Apollo 12, science became increasingly important to everybody within the organization. They realized that, yeah, we did what Kennedy asked us to do. We did the geopolitical thing, very, very important part of the Cold War psychology within the world's nations. But now let's get more out of it, and it really did take off, I think, from that point. That's the reason we had scientist astronauts, is because George Low and a few of the people around him were amenable to bringing that kind of expertise into the program. And when the National Academy made that recommendation to NASA that they select scientist astronauts, they had a friendly face and a friendly brain in George Low and Sam Phillips and others to do that. The main reason you want to send trained scientists or trained specialists into space to do whatever they are capable of doing as specialists is the same reason that you use test pilots early in a flight program, is that they have the kind of expertise necessary for that part of a program, and that was certainly appropriate for Apollo. But ultimately, we may have delayed a little bit too long in sending specialists to do the lunar science work, the field geology basically necessary to understand the moon. I think the main thing it has done is given us new insights, maybe not understanding, but insights into the early history of the Earth, the first billion years, because the moon has recorded what happened in the intersolar system during that period of time, and the Earth has destroyed it. It obviously happened on the Earth. The moon and the Earth have been co-orbiting for a long time, but right, almost certainly from almost the beginning of the solar system. So the moon is that kind of a record of history, particularly impact history. There's a basin on the moon that, again, hypothetically is about 3,200 kilometers in diameter, the Procolarum Basin. There is a well-recognized basin that's 2,500 kilometers in diameter called South Pole Aitken. And those kind of basins were forming in the first billion years here on Earth, as well as several hundred, probably several thousand basins that are at least 300 kilometers in diameter. That the Earth attracts far more of these asteroid impacts than the moon did. And that means that first billion years of time was very violent. Well, what else was happening? Complex organic molecules were getting organized at the same time and may even have become replicating during that period of time. Well, how did that happen? That's a question, not an answer. And we have to start thinking about that. Well, one of the possibilities is that in an aqueous environment, which the Earth is, when you create a lot of fine debris as a result of impacts, you're going to create a lot of clay. And clay, some forms of clay have very interesting properties in terms of organizing these organic molecules. They form a scaffolding, if you will, a substrate on which organic molecules can get organized and also start to pick up things like potassium, essential to life, and the like. And so it may well be that clay turns out, first of all, to be the dominant mineral species during this violent period, and two, it may be the basic catalyst that allowed life to begin here on Earth. And what do we see on Mars? Well, we see in the oldest rocks on Mars a significant amount of the right kind of clays. That's been detected by some of the orbiters that are now operating in the vicinity of Mars. The regolith, the debris layer covering the moon, which originates as a result of the superposition of various layers of ejecta, the maturation of each layer for a while, and then a new layer would come in. So it's a very complex stratigraphic or layered structure. And if that was happening, as we certainly thought it was, and know now that it did happen, then you're recording the history of the sun with each layer that time. If you can figure out a way to date those layers, then you start to understand how the sun has evolved over time. Well, I think we're finally getting to the point, particularly looking at the deep drill cores. The one that we took on Apollo 17 turns out to be the best. It's a complete core down to 3 meters depth. And if we start to look at those and the isotopic composition of various layers within that deep drill core, we're starting to see evidence, particularly in nitrogen ratios, that the sun is a primary reason for the maturity, the change in maturity of lunar soils, and that that ratio, that nitrogen 15 ratio, nitrogen 15, nitrogen 14 ratio, is an indicator of how active the sun was at any given time. Well, it turns out in that deep drill core we have a layer that can be dated roughly to about 500 million years ago, because we have dated a crater that almost certainly created that layer within the regolith. And now it's a very loose date right now. It's 500 plus or minus 200 million years, and it's done by a process that Cahill calls topographic diffusion. He has developed a technique by which he can estimate the ages of craters by how much they've degraded over time. Okay. And with that 500 million year date in the core, we now have a chance to see whether or not we can date layers younger and older than that date by how much they have matured under the sun. Well, it also turns out that about 500 million years, there's very strong evidence in these nitrogen ratios that the sun changed its luminosity about 500 million years ago. And so that the soils that we see at the surface today are more mature than you would have expected had the sun not increased its luminosity. And that's pretty good data. That we know. Now the question is, what else was happening in the Earth-Moon system 500 million years ago, approximately? Well, we had the Cambrian explosion of life, both in quantity and diversity. That happened about 500 million years ago. We need more precise dating than we have right now for that hypothesis to be proven. But it still is a very interesting indication that Shoemaker was right. And the reason we started taking cores of the lunar regolith was because Shoemaker believed that we would get the history of the sun out of those cores. Now, it took us practically the whole Apollo program to figure out how to take cores. The reason being that the regolith itself is very hard to core. It's incompressible, and almost every technique we tried to use ran into problems. But by Apollo 17, we were able to get a 3-meter core and get a number of these drive tube cores, one of which is just now being opened by NASA, and a lot of us are looking forward to seeing if we're going to gain more information, not only about the avalanche where it was collected, but maybe more information about the later history of the sun. Well, I've recommended, and still recommend, that NASA look very closely at the management environment that existed at the peak of Apollo, when we finally learned everything we needed to know in order to conduct a very complex, high-risk program of going to the moon and returning safely to Earth, John Kennedy's challenge to us. And we did that, and there were a number of ingredients in that environment that I think really need to be replicated to the degree possible. Number one, everybody was young. The average age of engineers, both in the private sector and in NASA, some 450,000 people, the average age was in the 20s. These were really young. The astronauts were among the older people, and the middle-level managers that were making everything happen were in their 30s. So that may be one of the, if not the most important ingredient, certainly one of them. The other is we had a management reserve that allowed us to stay on schedule, that avoided the political pitfalls of getting off schedule. That reserve was the baby, if you will, of Jim Webb, the Kennedy's administrator of NASA. He asked his engineers what they thought carrying out Kennedy's challenge of landing a man on the moon, returning him safely to Earth, would cost. And those year dollars, they came in plus or minus about $1 billion at about $8 billion. Well, when Jim Webb went to the OMB and went to Congress, he said 16. He doubled it. And so we were roughly dealing with 100% management reserve, and we used all of it. We really did. Because there's always unknown unknowns you come across in those kind of situations that have to be dealt with. And if you don't have the money to deal with them, you're going to slip schedule. There's just no other way to do it. And so that particular reserve was very important to Apollo. There were many others. Partly because everybody was young and the management had not gotten overly complex, a good idea could move very quickly to a decision. And sometimes overnight, these decisions were made. And that meant that the whole program was very efficient at dealing with test results that were adverse or with new ideas and things like that about how to accomplish the mission. And of course, extremely important was the ability to build a rocket with the capability of the Saturn V. That actually started in the Eisenhower administration. Ike, in January of 1960, over a year before Kennedy made his challenge to us, Ike ordered T. Keith Glennon, the then administrator of NASA, to begin the development of what was then called the Super Booster. That, there was another name, the C4, because it had 4 F-1 engines in the first stage. That began the Saturn V well in advance of Kennedy's announcement. Had that not started under the Eisenhower administration, we probably couldn't have made the end of the decade schedule that Kennedy had asked us to. The role of a national space agency is geopolitical. The country has to take into account the activities of other nations, and in this case, particularly China. And so NASA is really a geopolitical entity. It was in Apollo, it has been since, and will be in the future. What is different now relative to Apollo is that there are commercial providers of launch services that did not exist at the time of Apollo. Those commercial providers, SpaceX, Blue Origin, and potentially others, can be a very important part of the future program, Artemis or whatever programs you have, and potentially can be much more efficient than a government agency in developing launch vehicles. The big challenge, though, for these commercial providers is to manage risks at a level that politically is viable. You're never going to eliminate the risks of going into space, and going into deep space enhances those risks significantly. That hasn't changed. The risks that Apollo had to manage in deep space are still there. That hasn't changed. The engineering capability to manage those risks has changed. We have a lot of new technologies we can use, but still the risks are still there. I'm not absolutely convinced yet that the private sector has come to grips with how to best manage the risks of launch, of operating in deep space, and so forth. And NASA has to be very careful as they integrate so-called commercial activities. They're not all commercial because there's a great deal of subsidy going on here. But nevertheless, of integrating those kind of capabilities with their programs to make sure that the risks are still being managed appropriately. That is a political thing. One of the biggest risk is political risk, and you manage that by managing other risks. The most important sample was with respect to resources on the moon was collected by Neil Armstrong 50 years ago. This is the year of the 50th anniversary of Apollo 11. Neil and I worked together a great deal before and after his missions. And one time I asked him, why did he fill the rock box with dirt, with lunar dirt? And he said it looked empty at the time. He had put a really amazing collection of basalts and regolith breccias into that box, but it still, to him, looked empty. So he filled it with 100084. We like to talk in numbers in this sample world. But that 100084 really was the first major sample that showed us what kind of resources did exist in the lunar regolith. And that included all the resources that you need to operate in space. Hydrogen, water, because you can, if you heat the soil, which has oxygen in it, you will produce some of the hydrogen will come off as water. It has oxygen and nitrogen and carbon compounds. These are very important to the future of operating and living in space. And so that sample 50 years ago started to tell us that the moon could play, and almost certainly needs to play, a major role in human activity on into the future as it encompasses this so-called new ocean of space. In addition, that sample showed that there was helium in the soil, and a significant amount of a light isotope of helium called helium-3. Helium-3 is an ideal fuel for fusion power once the technologies are developed in order to use it. Fused with itself, it produces no radioactivity. Fused with deuterium, it produces a very small amount of residual radioactivity in the reactor itself. And the radioactivity comes from having neutrons. And when you don't have neutrons, or what they call aneutronic fusion, then you don't produce any radioactive waste that you have to deal with. It also can be much more efficient because you can convert the fusion products directly to electricity. You don't have to go through a heat cycle in order to produce power. So if you had it here on Earth, we'd be using it today, I'm convinced. But you don't have it here. It's just not available. The atmosphere and the magnetosphere of the Earth keep helium-3 ions from being available. The moon does collect these helium-3 ions, and there is enough to potentially be commercially viable. The private sector investors might well, at some point in the future, see that there is a value to harvesting helium-3 from the moon and using it in fusion reactors here on Earth. Helium-3 has another interesting application, side benefit. If you have it coming back to Earth, it can be used for lung diagnostics. It is an ideal way to get very high-resolution images of the human lung because it can be polarized. And as a result, you can start to deal with this extraordinary threat human beings have of lung cancer. If you can diagnose lung cancer early through helium-3 diagnostics, then you have an opportunity to cure. Right now, only 19% of people who develop lung cancer survive. That's the worst record of any cancer that we have, practically any cancer, with maybe the exception of pancreatic cancer. And so the advantage of having helium-3 back here on Earth are really immense. Now, can you do it in a cost-effective way? And that's the question. But once you are established producing resources on the moon, then a lot of things start to become possible, including Mars exploration. People who think you're going to go directly to Mars, I think are whistling Dixie, pardon the expression. It's going to be very, very tough. Mars is a long way away. One way of shortening the transit time is helium-3 fusion rockets. And to shorten that so your exposure to space radiation is less. And the adverse effects of microgravity or zero gravity. Mars also has only enough atmosphere to cause problems and not enough to help you dissipate energy as you enter it, like the Earth does. And so we need to deal with all of those new engineering challenges, operationally as well as from the physiologically. And I think we will. I think we'll figure all that out. But the moon is in the critical path to figuring those kind of things out. it's very important to recognize that one of the successful ingredients of Apollo was the response of young people to Sputnik 1. The launch of Sputnik 1 created what has correctly been called the Sputnik generation. Many, many young men and some young women became extremely interested in space. The October Skies movie is an excellent example of that kind of interest, but it was throughout the country. And those young men mostly came into Apollo as the engineers and to some degree the scientists of Apollo. They joined with a generation that was coming out of World War II with significant management experience, joined with another generation that had populated the National Advisory Committee on Aeronautics, which provided the core management capability, really coming out of the management that the Space Task Group had exerted on the X-15 program. That's where a lot was learned, but you really had this core foundation of young people who were interested in engineering, who had the mathematical tools in order to participate in engineering and to participate in Apollo. That base, I think, is still there. It just has to be mobilized. The key element, though, in any education program, we talk about STEM, but it's the M that is key. If you do not have, as an individual or as a country, a strong base in mathematical fluency, then all sorts of things become impossible. As an individual, there are whole careers that you can't even entertain entering if you don't have a mathematical background, a strong mathematical background. Now, the other things, the science technology side of things, it's wonderful to have. It shows you how to apply mathematical tools. Most of that you gain, though, once you go out and really start working in engineering. It's like people try to teach systems engineering. You can't teach systems engineering, in my opinion. You got to learn systems engineering in the real world. And I think Apollo showed that in spades. We created systems engineers that had never even knew what that phrase meant, out of the strong base of education that came out of World War II, the Cold War, and also the launch of Sputnik 1.